Today we're going to embark on a comprehensive discussion regarding the portfolio optimization approach with a specific and crucial focus on achieving the maximum Sharpe ratio. Our exploration will, as is our established practice, involve practical work and reference materials sourced directly from the invaluable Finance ResearchGate website. The absolutely essential first step in this entire process is to thoroughly comprehend the intricate mathematical foundations and underlying principles that truly drive this powerful concept. What exactly defines a Sharpe ratio? It's fundamentally a simple ratio comparing the excess return generated by a portfolio against its associated portfolio variance. So, to begin, the equation we're examining here starts with the portfolio's excess return. The capital letter E, as you can see, specifically refers to the concept of excess return. This essentially means that to calculate this value, we take the overall portfolio's total return and then subtract the prevailing risk-free rate from that particular value. And then, as the next step, we divide this result by the standard deviation of the entire portfolio.
Consequently, what we are observing here will accurately represent the precise gradient or steepness of this particular line.
A steeper slope indicates that we are achieving a greater return in proportion to the level of risk taken. Therefore, the Sharpe ratio essentially serves as a straightforward measure of the return generated for each unit of risk undertaken. The key factor isn't simply the overall length of this specific line. It's also not about your specific placement or where you are on this line. For example, we cannot simply increase our financial leverage and then invest more aggressively while remaining on this specific line. Ultimately, the Sharpe ratio's true meaning and value are determined by its slope. So, if we consider the highest possible slope, this particular point would represent the absolute maximum Sharpe ratio achievable. Therefore, within the context of this specific situation, it's important to note that the Sharpe ratio itself is not influenced by or dependent upon the magnitude of the scaled weights. For instance, if you were to adjust the weights of your portfolio in any manner and you selected a scaling factor, let's say C, this particular action would not have any impact on the overall Sharpe ratio, primarily because its effect would simply be nullified from the numerator and the denominator. So when you scale the weight, you are applying that adjustment in both of those positions. The scaling effect on the numerator and the denominator will then be completely cancelled out, and the Sharpe ratio itself will remain exactly the same. Therefore, it is inherently a scale invariant measure. And as a direct consequence of this, we are fully prepared to strategically leverage that information to our distinct advantage, enabling us to meticulously solve and ultimately pinpoint the absolute optimal maximum Sharpe ratio.
In this case, we are going to rectify the problem.
One of the numerator items,
settling at a consistent, steady value.
And then, as a subsequent and very important step in our analytical approach, we will proceed to effectively minimize the variance. So, because the entire problem fundamentally revolves around the specific ratio, we are able to establish this particular component as a constant, and then, with that in place, we can effectively proceed to minimize this other critical aspect. This approach will ultimately result in achieving the highest possible ratio. Alternatively, we could reverse our strategy. We would hold the standard deviation constant and then focus on maximizing the excess return. Regardless of the specific method chosen, our primary objective remains the maximization of this crucial ratio. So let's, in this particular instance, proceed with this specific scenario. Our current task involves making adjustments to the numerator
And
our main focus is on minimizing the potential risk.
So we are minimizing the risk, focusing on this specific area.
We're looking at a situation where there's a specific constraint, meaning we have a fixed constant value. For instance, let's assume this constant value is set to 1, or really any numerical value we choose. In such cases, we can then proceed to utilize the Lagrangian function. And the way this Lagrangian function operates is quite straightforward, as follows. We start by identifying the main objective, which is to either minimize or maximize. In this specific case, we aim to minimize this particular part, so we write it down, then add a minus sign because we are minimizing the objective function here. Next, we introduce the Lagrange multiplier, often denoted as lambda, and then we multiply it by the constraint function. This particular constraint, as it's currently formulated, involves an equality sign, specifically stating that it is equal to 1. However, for us to properly incorporate this into our optimization equation, it becomes absolutely essential that we rearrange it so that the entire right-hand side is set to 0. First, we simply need to shift the number 1 over to the left-hand side of the equation, so that would then become negative 1 equals 0. And then, after that, we'll take this entire part that we've just moved down, and we will multiply it by our lambda variable. And then we proceed to calculate the first derivative of the Lagrangian function, specifically with respect to the weight vector w, given that the portfolio optimization problem is ultimately solved by determining these optimal weights. because the portfolio's central objective is to accurately determine the precise weighting that we must apply to our various input assets. So, when we compute the first derivative with respect to our variable w, that particular term would then resolve to 2 times the variance-covariance matrix, and this entire resulting expression is then multiplied by the w weight vector. The reason we have this 2 here is because we're working with 2 terms of w, and when we take the derivative of that, it will become 2. Oh, sorry, I mean that's w squared. So when we actually take the derivative of w squared, it will become 2 multiplied by w, which is precisely the term that you can see right here and also over here. Of course, we must not forget the variance-covariance matrix, because it is also being treated as a constant value since we are taking the derivative with respect to w. And when we proceed to take the derivative of this particular part, we will then obtain this specific term. It's important to remember that E represents the excess return, not simply the unadjusted raw return from the invested assets. Then we can easily solve this equation, which will allow us to obtain this specific and useful form. So, the optimal weight can be determined quite easily if we first invert the variance-covariance matrix and then proceed to multiply it by the vector representing the excess return. To illustrate this point, let's consider a scenario where we have 3 distinct investment assets. These assets generate raw returns of 8%, 12%, and 6% respectively for each of them. Additionally, the current risk-free rate is set at 2%. Alright, so the very first step we need to accomplish here is to accurately determine the vector of excess return. To achieve this, we must subtract the risk-free rate from each individual asset's raw return. Once that calculation is complete, we will then have our resulting column matrix. And let's assume the covariance matrix is the one we're looking at here. This matrix will then illustrate how the various assets interact and co-move with one another. So what we'll have is the variance of the first asset, then the covariance between the first and second asset, and then the covariance between the first and third asset, and so on. Let's carefully consider and count the number of unique and distinct terms that are present within this particular matrix. We can clearly identify them one by one. We have the first term, then the second, followed by the third, the fourth, the fifth, and finally the sixth term. So it's like we have a diagonal line. Everything that appears above it is a repetition of what's on the other side. Essentially, it's as if we have a mirror image right here. Why? Because the 0.08, for example, which is the covariance between the second asset and the first asset, also appears here, the covariance between the first and second asset. Same thing for the other numbers. So if you want to determine the precise number of distinct terms that are actually present within the variance-covariance matrix, you simply need to take the total number of assets, multiply that by the number of assets plus 1, and then divide by
Number 2.
So in this particular scenario, we're looking at 3 multiplied by 4, and then that result is divided by 2. This calculation will ultimately result in a total of 6 unique and distinct terms. If we have more assets, the covariance matrix will become significantly larger. Consequently, we'll need to employ a longer historical period to properly estimate all the parameters, including the variances and covariances. Now, if we then take the inverse of this, we will end up with this inverted matrix. Once the inversion process has been thoroughly completed, we then proceed to perform a straightforward multiplication operation, taking the resulting matrix and multiplying it by the column vector that represents the excess return. This here one. And that will give you the z-score, which is essentially just the weight once we have standardized it. So these are what we call the z-values. To perform this standardization, we calculate the proportion in relation to the overall total. Therefore, if you were to sum them up, if you were to add all the z-values, then we would arrive at a figure, for instance, 2.3. So Z1 is for the first asset, the second asset is also here, and then the third asset. To determine the precise weight, we first need to standardize and then calculate its proportion. For example, if you divide this specific value by the overall total amount, you'll obtain 0.33, and similarly for all other assets. Consequently, the entire sum of these proportions will equal 1. Guys, ansid pligi. So, let's take this concept and apply it directly. We'll use the Finance ResearchGate website and specifically navigate to its time series section. And then I'd like to begin our discussion, starting with the year 2000 and concluding in the year 2010. First, we need to ensure that this specific configuration is properly applied to our visual charts. And then, moving on to Series A, we will proceed to carefully select the stock's monthly return data. This is absolutely essential because our main objective is to accurately identify the maximum Sharpe ratio specifically for these stock returns. Okay, for this particular instance, let's select an entire market sector to identify the most optimal investment portfolio. We'll commence by looking at the consumer staples category. And then following that, we proceed to apply our established methodology. Therefore, for the purposes of our detailed analysis, we meticulously selected every single firm operating within this particular sector, covering a comprehensive period extending from the beginning of the year 2000 right up to the end of the year 2010, with all relevant data collected on a consistent monthly basis. These are precisely the companies that form the foundation of our study. And then, our next very important step will be to create a comprehensive portfolio. Our main objective for this analysis will be to achieve the maximum possible Sharpe ratio. To achieve this goal, we should proceed by utilizing the standard sample covariance estimator. There is absolutely no compelling reason to apply shrinkage to our variance covariance estimator unless we encounter significant issues or problems. The estimation look-back periods refer to the specific number of previous time frames or data points that you intend to incorporate into your overall calculation. To perform this estimation, we first need to calculate several key financial metrics. This includes determining the expected return, or in some cases, the excess return. Additionally, we must also compute the variances and the covariances of these financial instruments. Therefore, to accurately construct these crucial inputs, which will then populate the matrix that I presented to you previously, we absolutely require a comprehensive set of historical data points. So for our practical example, let's proceed by utilizing a period of 60. We will be utilizing the data from the most recent 60 observations, and subsequently our team will conduct a full portfolio optimization process at the end of every month. Consequently, this strategy entails that we will consistently rebalance our current holdings and then proceed to construct the identical portfolio structure repeatedly month after month. So, we're not just going to optimize a single portfolio once. Instead, we'll be optimizing one portfolio every single month, continuing this process right up until the very last month of the year 2010. For this particular scenario, let's strictly consider only long positions, which means that the assigned weight, represented by W, must always be positive. It absolutely cannot be negative in our calculations. If it's said to be negative, this clearly indicates that we are allowing for the possibility of short selling. As for the maximum weight, we need to raise this limit specifically to guarantee that our entire portfolio optimization strategy will not be restricted in any way. And here it's absolutely essential to properly establish the risk-free rate. When performing any portfolio optimization, it's imperative that we assign a precise numerical value, so the out-of-sample performance for the crucial Sharpe ratio can be accurately and reliably calculated. So just continuing with our previous example, let's confidently set that figure to be at 2%. So when we need to input the value, we should make sure to write the number followed by the percentage symbol. After that, we simply press enter, then just click your mouse somewhere outside of the input field. And so we should probably consider increasing the maximum number of assets allowed because, as you know, we've been working with over 120 different firms. And then once that's done, we can proceed to run the portfolio analysis. Please take note of the fact that our out-of-sample performance, and what that specifically means, is that if we were to maintain this portfolio for the entire duration of the very next month, immediately after we've built it, then the resultant Sharpe ratio, which is a key metric, is predicted to be exactly 0.26. So this figure here represents our annual Sharpe ratio, and as you can clearly see, it's on the lower side. It's crucial to remember that our investment strategy was specifically designed to target a very particular low-risk sector, namely consumer staples. Therefore, this inherently explains why the overall return we're observing here is naturally lower when compared to other potentially higher risk sectors. And here, within this table, we can observe the capital weight invested. For instance, considering the final month of the year 2010, naturally, we utilized data from the preceding 60 months to derive our parameters, and subsequently, we carried out the portfolio optimization process. These figures represent the specific investment weight allocated to each individual firm. At this point, we have the opportunity to construct an identical investment portfolio. However, we would then proceed to implement it within an entirely distinct economic sector. So let's proceed with that. Following this, we will naturally choose the very same input variable we've been working with, which is, of course, the monthly return data. After that, our next step involves applying a filter based on the specific sector. For this particular demonstration, let's go ahead and select the energy sector.
And then apply it.
Here, you can see the complete list of all the firms. You have the option to sort them in any way you find most useful. Overall, we've identified approximately 154 distinct firms that were active within this specific sector throughout the entire period from the year 2000 up to and including 2010. Let's start the portfolio optimization.
And the objective, once again, is to achieve the highest possible sharpness. We are going to consistently employ the same estimation look-back period, which is set at 6. Following this, we will rebalance our holdings every single month. Therefore, we'll be repeating this entire operational process repeatedly, month after month. Regarding the maximum weight, we need to adjust it upwards. This is crucial to ensure that our portfolio optimization model isn't artificially constrained by any upper limits. This way, the system will be free to assign any weight it deems appropriate based purely on the optimization results. For the risk-free rate, we'll set that to 2%. Once you've entered that, please hit enter and then click outside the box to confirm. And we need to increase that amount to ensure that every single asset is fully accounted for. Following that, we will then proceed to manage the entire portfolio.
It's important to observe that the out-of-sample performance for the energy sector, when we apply the maximum Sharpe ratio portfolio strategy, is yielding a significantly higher Sharpe ratio than what we observe in the consumer staples sector. If we examine this particular metric, its current value is precisely 0.81. This represents a substantial increase, standing at nearly 4 times the level observed within the consumer staples sector. Look, once again, we can clearly see the investment weight assigned to each asset for every single period. Therefore, in each of these periods, a complete portfolio optimization process is actively taking place. Also, please take note that the initial period we observe within this specific weight table actually commences from the year 2005 rather than beginning in the year 2000. The primary reason for this is that we required a full 5 years or precisely 60 months of continuous observations to establish our data. Consequently, we were unable to initiate our analysis from the year 2000 nor from 2001, 2002, 2003 or 2004. The earliest would be January of 2005, which means we have a sufficient number of past historical periods to accurately estimate the necessary parameters. These include the excess return as well as the variances and covariances. If we scroll down a bit further, we'll find this table here, which clearly presents all of the in-sample statistics. Once again, it's evident that the portfolio based on the Sharpe ratio consistently delivers a higher mean return. And even when we consider this relative to the inherent risk involved, if you calculate the proportion, you'll see that it's quite similar to the Sharpe ratio itself. Specifically, we observe that this value is notably higher when we focus on the energy sector. That's all we have for you today. Thank you for watching.